true. Although geometric proofs are kind of step-by-step, they're kind of hard because you have the given and then you have to figure out what to do in the middle. We're going to do another kind of proof today called proof by induction. I think it's more systematic than a geometric proof because they're the same every time, but it's definitely a little bit confusing. So please try to stay with me today. If I lose you for 2 minutes looking out the window or closing your eyes, you're going to have a really hard time getting back on track with us. So try to stay focused today. It's a tough day, but it's not impossible if you just write out some good notes, okay? Everything in math has a proof to go with it. Every single theorem that you've ever been given, I'll let you go ahead and have this so you can start writing it down. Like the Pythagorean theorem, all these formulas that I've given you so far, it only can be a formula or a theorem if it's been proven. Do we need to prove everything? No, because someone else has already proved it for us. That's what's so great about it. That's why it becomes a theorem. But it's important to kind of understand the process of how this works. And so today we're going to work on proving the sum of a geometric or arithmetic sequence, and how do we know that it works all the time? How do we know it works for every number that we can plug in? So to start this, we're just going to look at our own little sequence. So I started with, this is my first term, and then my second term, if I was adding them together, I'd have 1 plus 3, then 1 plus 3 plus 5, then 1 plus 3 plus 5 plus 7, right? You can see we're kind of just adding odd numbers here. Let's look at the sum of these, each of these terms. The sum of the first one, do you agree that's just 1? Yep, 1's just 1. If I look at the second one and I want to add that up, 1 plus 3, that's going to be 4. If I look at the next term, 1 plus 3 plus 5, do you agree that that looks like that's going to be 9? Not looks like it, it is going to be 9. If I add this up, I think that's going to be 16. You notice anything about these numbers? Yeah, I think they're perfect squares, which means it looks like, from what I have here, that if I added up the first 5 terms, I'm guessing it's going to be 25, would be the next one, because it kind of looks like that this is n squared. Notice that for the 4th term, it's 4 squared. For the 3rd term, it's 3 squared. Oh, interesting. We could also try to come up with a formula. I'm not really focused on this too much because they're going to give you all this. You don't have to come up with it. We could also come up with a formula for the nth term. What would be the formula for how I could get 3 or how I could get 5 for the 3rd term, or 4 and the 7? How do those go together? We could use our formula, our arithmetic sequence formula. But do you agree that this number is twice this number minus 1? Do you agree with me on those? The last number compared to this? We could say that the nth term is 2 times n minus 1. And again, you don't have to worry about this part so much. I'm just trying to show you where this stuff's coming from. This number, to find 7, I could take the 4 times 2 and subtract 1. For this one, to find the last number, I could take 3 times 2 and subtract 1. Right? You kind of follow me on that? It seems like maybe we could summarize this sequence with this lovely little formula that I wrote out. That for the nth term, we could say if we have 1 plus 3 plus 5 plus 7 plus so on and so on, that whatever n was, that last number would be 2 times n minus 1. And it also seems that the sum, if we add all those up, will always equal n squared. This is what seems to happen, or what appears to happen. But in math, you can't just say it worked for 4 of them, it worked for all of them. So we're not allowed to jump to the conclusion to say this works for every number. There has to be a proof that goes with it. Oh, I do that whether I'm recording or not, just so you know. It's just because I hit this a lot and then this falls down. That's why I do it. Oh, well then maybe it's just a nervous habit I have. Why is it okay? Why is it not okay to jump to this conclusion? Because we don't know that it works for every number. And the great example of this, and it's up to you if you want to write this down, this is just my example of why do we have proof, is this guy, Pierre de Fermat. Not Fermat, he's French. This is called Fermat's last theorem. Why do you think it was called his last theorem? He died before he could even prove that it was true. So for years, many other mathematicians worked really hard to try to prove Fermat's last theorem. And I don't think it was proven until I don't know when. I can't make up a date. But it was a long time after he died. But he proposed this possible theorem. He said for any number, f sub n, if you take 2 to the 2 to the n, how about that? 2 to the 2 to the n. So it's like a double exponent. And you add 1, he said that you will always get a prime number. Fermat's kind of old, so he didn't have all the technology that we have now that probably he could have proved this or disproved it a lot quicker. But he just worked through this, and he said, let me try to see how I can prove this. I'm going to show you what the first few numbers are. Again, just to kind of show you where this comes from. I'm not going to really spend time working every single one of these out. But just to show you, if you plug 0 in here, you'd get 2 to the 2 to the 0 plus 1. Kind of a weird thing. We don't do a double exponent very often. But 2 to the 0 is 1. So then you would be left with 2 plus 1, and you'd get 3. That works. That's a prime number. If you plugged 1 in there for n, you'd get 2 to the 2 to the first, which would be 2 squared. 4 plus 1 is 5. So 3 and 5, those are both prime numbers. Those are easily proven. Very quickly, they get very big. I'm not going to waste time working it out for you. But the next number is 17. Also a prime number. The next number is 257. Then we get 65,537. And think about Fermat living back a long, long time ago. He was working out to see, are there any numbers that go into 65,537? Like he was trying to show that that was always a prime number. And then the fifth one is 4,294,967,297. And he died before he could prove that that was also a prime number or come up with the algebra to show that it's a prime or not prime. And actually, another mathematician, Euler, that we've talked about, he actually proved that this is not prime. So poor Fermat died thinking that this theorem was going to be true, but it wasn't, because, I'll even tell you, that this factors into 641 times 6,700,417. Who would have thought? Which means that this is not a true theorem. I told you you didn't have to write it down. I said that from the beginning of when I started. When I said you don't have to write this down, I think I've said it 2 or 3 times. I said it when I showed you this. I said it when I showed you the 0 through 5. You don't have to write this down. I'm just trying to show you the reason that we have proof. So the first 4 are prime numbers, but we can't say that this is true, right? This is not a true theorem. So that's why we have proof, all right? In math, are you ever going to prove anything or try to prove something that hasn't been proven before? Probably not. But we're going to go through this process because proof is a really important part of math, okay? I don't know how he died. Probably stress of trying to prove this. So here we go, mathematical induction. You need to write this one down. This one's not an option. This is the definition of math induction. It's clear as mud. So you write it down and then we'll talk about it. What?
I feel like the word mathematical should kind of be in it.
It really does, doesn't it? No?
Yeah, it does. Right now, like,
Oh.
it's really weird to write. So
Mathematical. You have to take the pause there. Mathematical. Pythagorean theorem has some really cool proofs to it. Like you can prove Pythagorean theorems in really cool ways. Much more cooler than math proof by induction. In geometry, people kind of have nightmares about proofs after geometry class. The great thing about proof by induction is you always have these two steps, and although it's a little crazy the first time you do it, and you're like, where in the world did I get this from? Once we're going to do two today together. Once you do one of them, every one is the same setup. And so that's what's great about it, because in geometry, you have your givens, and you know what you're trying to prove, but the middle could kind of go a million different ways. For us, it's going to be the same every time. And to prove that something is true, what we're going to prove are those formulas, like what I started with, like the sum of something equals this. So we're going to look at sequences. Every time, step one is we're going to prove that it works for 1. So we're going to plug 1 in and show that it works. And honestly, that's like your given step. It's like the easy step. It's the step that if you have no clue what you're doing on the test, you do step 1 and you leave the rest blank and you miss less points. But you at least get a couple. Well, you know, maybe 1. Maybe 1. Then step 2 is a lot bigger step, but every time, what we're going to do is we're going to assume that it's true for p sub k. K is some arbitrary term. And then if it's true for that, we're going to show that p sub k plus 1 is also true. So basically, we're going to take any term, and we're going to prove that the next term is also true. And it's kind of just a bunch of algebra. We're trying to make stuff balance and match each other. That's about as clear as I can make it till we actually do one. But what does this mean? P sub k and p sub k plus 1? We're going to start without a proof, and we're going to start with just this. Not a proof. What? I don't know. We'll see how fast this goes. They had about 4 minutes left in second hour, I think.
That's a 4 enough to get the first note.
Maybe. So first of all, you got to understand what it means to go from k to k plus 1, and it really just means going the next step. If this is p sub k, this is a lovely little formula. Notice that there's k's all the way through here. What do you think I'm going to do to find the k plus 1 term? If I want to go 1 more than k, add 1 to k at the end, right? Like I can't just add 1 out here. It's kind of like f of x. If I said this is f of x equals x squared plus 1, do you agree that f of x plus 1, I replace every x with x plus 1? You follow me on that? Right? That's what we're going to do for the k plus 1 term. You don't just add 1 to the end. You add, every k becomes a k plus 1. So this k is going to become k plus 1 squared. I'm going to show lots of work, even though I know you're going to just add it up on your homework in your head, and I'm totally okay with that. But I want to show you where this is coming from in your notes. This k is also going to become k plus 1, but then there's still a plus 1 out there. So every k is being replaced by k plus 1. The good news is you don't have to FOIL all this out. I mean, I guess if you really want to, you can. But we're just trying to replace k with k plus 1 and sort of simplify it. Which means I would write this as k plus 1 squared times k plus 2 squared all over 4. That would be the term after p sub k. That would be the p sub k plus 1. Well, this is not a proof. We're just practicing. Yes, if they give you p sub k to find k plus 1, all you do is replace k with k plus 1.
So that would give you like before when I was before.
No. This is just some random thing. These numbers are going to change every time, but the process is the same. You replace k with k plus 1.
How come you want to put the
Because this is all addition, right? Like this is all still together, so I guess you could think about it like this, but it's just addition. You don't need parentheses because you can add like terms together. This was squared, so I had to make sure I squared the whole thing. This one isn't squared until I close that parenthesis at the end, so that's why you can add those together. Other questions about that? We're gonna keep doing this as we go through the proofs, but that's a really important step in order to do these proofs.
So just another way again where you got the like the extra one.
Because it just said find k plus 1, right? So every k, like how do I get this extra 1 over here? Is that what you mean? Because this k becomes k plus 1. But there's still a plus 1 out here that has to stay there. Right? Alright, here's a proof. This is what it's going to say in your homework. This is why I didn't print your notes out for you, because this is pretty much it. This is all I would print, and then we're going to write everything. Right, I just print this. Notice that this is what we've been doing. We've been adding up sequences. We've been writing formulas for the nth term. We're now going to prove that the nth term is equal to the sum. We're going to prove that this actually works. So notice they give me a lovely little formula. 3 plus 7 plus 11 plus 15. This is the nth term. Like if I wanted to find the 10th term, I could plug 10 in here. If I wanted to find the 100th term, I could plug 100 in here. And then on this side, this is telling you what the sum equals. If you add up however many terms you have in terms, this is what the sum is supposed to equal. We're trying to prove that this works for every number. We can't just plug numbers in because we would never run out of numbers to plug in, and we could never prove it like that, which is why we have proof by induction. And every time, the most important thing is that you're showing me the proof. It's like geometry. I don't know if you remember much about these proofs, but you know the givens, and you know what your end statement's supposed to be. Like, you could always write what you're trying to prove, but it's the middle that means the most. And it's the same thing with these. You know it's going to work, or we're going to find out pretty soon they're always going to work. They're not going to give you one that's impossible. That would be terrible of me to do. So it's going to be easy to, like, make up work in the middle and draw the line and be like, oh, I did it. The middle work is what I'm grading. So if you don't have the work and you don't have the steps, you're not going to get the points. So don't skip steps in a proof. I need to see what you're doing, okay? So you should be writing these the exact same way that I write them. Step 1, prove for P sub 1. And I write that every time on my paper. Normally I don't write step 1. Normally I write this. 1, prove for P sub 1. And you're going to write that on your paper every time you're doing a proof. And it's the easiest step. Because all you got to do to prove for P sub 1 is plug 1 in for both of these equations and show me that you get the same thing. So if I plug 1 in here, I'm going to get 4 times 1 minus 1 equals 1 times 2 times 1 plus 1. You don't have to show me a lot of steps in there. You can if you want. But show me that you're plugging it into the formula. And then say 4 minus 1 is 3. That's good. 2 times 1 is 2 plus 1, which is 3 times 1. 3 equals 3. Hooray, I did step 1. No, but I like to put a check mark. Check marks make me feel like I've accomplished something. That's very confusing.
It is. She's like, I can't believe check marks. And she's like, oh, that means there's something wrong.
Come on, what's wrong with those people?
English. They're English.
Step 2, and again, I write this. I don't write step 2. I usually just put a 2, but I write prove true for P sub k plus 1. We don't have a P sub k in our problem, so every time we need to make a P sub k in our problem. So we're going to say every time, we're going to write this, and then we're going to say, let's assume that P sub k is true. class in college called Intro to Abstract Algebra, and it was a whole class of proofs. Like the whole semester, all we did is proofs. And I feel like I wrote "let's assume" a million times that semester. Let's assume. Well, in math and in proof, we like to assume that P sub k is true. Is there a P sub k in this problem right now? No, there's a P sub n. How do you think I could get P sub k from P sub n? You just make the n's a k. You with me on that? Because we have to use k's. That's just how we do proof by induction.
So you do actually have to use k for this?
Yes. We're going to use k every time. So all I'm going to do is rewrite this. I'm going to say 3 plus 7 plus 11 plus 15 plus dot 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 plus, how do I make it into k's? I just change it. 4k minus 1 equals k times 2k plus 1. You could really use whatever letter you want besides n. The reason that we use k and not n is because k is some arbitrary term. N is like the nth term. K is like, what if it was the third term? What if it was the fifth term? So that's why we don't use n. You could use another letter if you want, but I always use k. So I just recommend using k. So we're assuming that this is true. Okay, that's kind of an important step. And then this is where I break this up into two parts. I have the end result, and then the going back and showing that it's true. Why do I break it up in two parts? Because I can't fit it all on one line of my paper. So this is how I've always done it, because otherwise it doesn't fit, okay? So we're trying to find the k plus 1 term for both parts of this formula. We want to find the k plus 1 term for this, and we want to find the k plus 1 term for this. And we want to show that those equal each other, that the sum of the k plus 1 term is equal to this sum over here. So I always start with this, and I'm going to write this in for your notes. I'm going to say, we are trying to show, or trying to prove, if we want to use that word. No, this is kind of like my notes talk here. I don't usually write this on my paper, so we'll put brackets around it. But you can write it if you want. We're trying to show what the k plus 1 sum will equal. So every time after I write my p sub k term, underneath it, I write what I'm trying to get at the end of this. And what do you think I'm going to do to get k plus 1 into this part over here on the other side of the equal sign? Substitute k plus 1 for k. And I probably didn't make myself enough room. Good thing I can just move all this. So I'm going to replace k with k plus 1. I'm going to replace this k with k plus 1. But everything else stays the same. All I do to get the k plus 1 sum is replace k with k plus 1. And then you might want to clean it up a little bit. At some point, you might have to go back and do a little bit more work. This would be 2k plus 2 plus 1. Or I would get k plus 1 times 2k plus 3. Everyone with me on that work? What does this represent? This represents if I did one more term, what the sum would add up to. This is my end result I'm trying to get to later. Again, it would be great if I could write this all in one line, but I've never been able to fit it once. Yes. We do. That's what we're gonna go back and do now. So this is where I split it up. So I like to do the end part first because I feel like it's less work, and I always put it over here. And then now I'm gonna go back and do exactly what you said. Now I got to do the k plus 1 over here for this part, which means I have to rewrite this whole pattern and then add the next term as well. So now I'm going to come back over here because that's how we do it. No, let me write it and then I'll show you, okay? Because the next term in the pattern, you have to include the other ones. Like, do you agree that this formula is representing when you add all these up? If I didn't include all these again and I just wrote the next term, that's not going to equal the sum. It's just going to equal the next term. So it's important that you rewrite everything. If you want the p sub k plus 1 term, you got to take everything that's there already and then add the next term. That's why you have to write the whole thing. You can kind of get lazy if you want. You can write 3 plus 7 plus dot 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 if you want, since we kind of know what's there. Plus 4k minus 1. Ooh, let's think about this. This is the kind of tricky part, I guess. This is why I do this last. I want the next term after this. If this is the kth term, I still need that. Plus, what is the next k plus 1 term? That's when you're going to plug in the k plus 1. So it's not just replacing k with k plus 1. When you're writing out the whole pattern, this is the kth term. The next term is going to be 4 times k plus 1 minus 1. All right? Again, the first one is the hardest one because it's kind of like, where's all this coming from? But every single proof, we're going to do another one after this. It's going to go much quicker because every single time it's the same way. You rewrite everything that's there, and then you do the next term by replacing k with k plus 1. We're almost done. This is the home stretch here, kids. Let me erase this, because I don't like that on my proof. So, how do I add this up? That's the next question. This is where our assumption comes into play. Do we know what this is right now? Forget about the extra part we added. Do we have this written somewhere else in our proof already? Was this the original problem? I just changed the n's to k's. Could I say that all of this is the same as p sub k, and then my extra term, which is 4k plus 4 minus 1 if I distribute?
So on our homework, are we not gonna have to do that for 1 hour? Just gonna be able to write it like the bottom of the unit.
I don't know. I always write it so you can show where it's coming from. But I guess I'm okay with that if you wrote p sub k there. Do I know what the sum of p sub k is? P sub k, we said we're assuming this is true. We know that it equals this. I wouldn't write this on your proof on your homework, but maybe you want to write this in right now so you know where this comes from. But if p sub k adds up to this, can I plug this in right here for p sub k? Yes, that's where that assumption is really important for this proof. So you might want to draw a line on your notes so you can see where that comes from. But I can replace p sub k with what it equals, which was k times 2k plus 1 plus, what do I have over here? 4k plus 3. Every single time, that's what you're going to do. Your formula is always p sub k plus your next term. Every time you know what that equals and you can plug it in, and look what we're left with. Could we simplify this and get an equation in terms of k? Yes, all we have now are numbers and k's. So I get 2k squared plus k plus 4k plus 3, which I think gives me 2k squared plus 5k plus 3. So what does that tell me? Here's what should happen. What we get here is supposed to equal our end result over here. This is why I like to separate it, because it leaves me more room over here. I got two options. Those don't look the same right now. I could factor this and try to make it equal this, or maybe easier, could I multiply this out and see if it equals this? Yeah, I think it does. I get 2k squared plus 3k plus 2k plus 3, or 2k squared plus 5k plus 3. What should happen every single time is when you do the k plus 1 in the pattern, and when you do the k plus 1 sum, you're proving that those are equal to the same thing for any k value. So how do I end my proof? I circle both of these, and I draw a little line, and I say, check. Or smiley face. Yes, it will work. Are there proofs that don't work? Yes. We're not working on proofs that don't work, which means ours should always work. Which means you know what's supposed to happen, which is why this work in the middle is what means a lot to me. If you just have this at the end, like you do this part and then you make up this part to make it work, I am going to be checking your work. It's kind of important that we do this.
So it's only true of any theorem nowadays.
No, there's lots of different ways to prove. This is just one way to prove.
Is this the simplest way to prove it?
Probably. It is very important that you do your proofs like this. I know some people like to write long and this way instead of this way. You gotta do your proofs like this. Like there's no making a big mess and then saying, well, I really did have it. You gotta do this. So let's do another one. Oh wait, hold on. How about this? I took this from another teacher that was talking about how to make proof by induction make sense to you. And I don't know, you're just gonna argue with me on this too. But here's the idea of proof by induction before we do another one. To prove that you could climb a ladder with infinite rungs, that's kind of what we're trying to prove that we could add up something that goes on forever. It says I'm going to do two things. One, I'm going to show you that I can get on the ladder, that I can climb on the first step. That's like our first step in our proofs, right? Proof for one. Second, I'm going to show you that if I'm on any rung of the ladder, that's the kth one, that I could get to the next rung. Which means for any k rung of the ladder, I could step up to the next one. And they say that if that's true, then that's going to guarantee that you could climb an infinite ladder. And I don't want an argument that you're going to die before you get to the top. That's the idea of proof by induction. I feel like this...
Technically, you can never get to the top. I feel you. It's false.
But do you agree that that would prove that that would be possible to do? Forget about that you would die and there's never a top to it. The idea is the sequence goes on forever. So it's supposed to try to make those k and k plus 1 things make sense. You could argue forever about it, but whatever. Write this in.
Holy crap.
Don't be scared of fractions. This one, well, it's just to show you where the formula comes from, but yes.
Can't we just say 1 plus 1 since 1 over 1?
If you want to, why do they write it like that? So you can see where the formula is coming from, right?
Okay.
Right.
I'm sorry, I did something that was unholy and an outline.
Notice a couple things. One, yes, they're fractions. But the biggest thing I want you to notice, these are multiplied, not added. So it's really important when you start writing out your k plus 1 term, you're not putting plus signs in between there because that's going to mess everything up. But I'm just going to start my proof. Step 1, I'm going to prove this for p sub 1. So that means I'm going to plug in 1 plus 1 over 1 is equal to 1 plus 1. Because that's step 1. Prove that it's true for the first term. So you plug in 1 every time. That's step 1. Prove for p sub 1, which means you replace n with 1, and you get 2 equals 2. You just completed step 1. That's proving that you can get on the ladder. Step 2. Prove for p sub k plus 1. My advice to you today when you're doing your homework is use your examples. Hopefully, by the end of your homework, that you don't have to look at it every single step. You can try to do a little bit on your own, but definitely use your examples because that's how you learn the process, because it's the same every time. Every time I'm going to write this, I don't have a p sub k, so I have to say, let's assume that p sub k is true. And if you notice, when you compare these two proofs that we're doing, I do them the exact same way every time.
So we have to write what's the same.
Yes. Because if we don't assume that it's true, then we can't substitute it in later. So kind of like a step in our proof. And what am I going to do next? I'm going to say, what does P sub k equal? How do I get P sub k? Just the same equation, changing our n's to k's, right? Because k is some different rung on the ladder. Here's where you don't have to write so much. Like for me, I'm going to say 1 plus 1 over 1 times 1 plus 1 over 2, and I'm done with that, dot, dot, dot. 1 plus 1 over k equals k plus 1. Not only is this important because we have to substitute in later, it's really important because we need that sum of P sub k, and so this is a really important step to include. This is where I break it up into two parts. I like to start with my end part. Maybe you want to do the k plus 1 over there first, you can. But I always feel like this is less complicated. So I want to find what is the sum of the k plus 1 term. And what would I do here to get that next sum? Plug in k plus 1 for k. And I'm okay if you just write the answer, but I'm going to write it as k plus 1 plus 1. Because I'm replacing k with k plus 1. Which means I like doing this because it tells me what I'm supposed to get later. That means when I go back over to the other part of my paper, I got to get k plus 2. Yes? Every time. Notice, same idea, just a different problem. So now I'm going to come over here, and I'm going to do the k plus 1 term.
You know, you're right. I really thought I hated geometry proofs. I learned this so terrible.
I like this one.
I do too. Use no guessing, like you know what to do every time. Every time I write this out, Janet, I don't think I'm going to mark it wrong if you know that you're going to plug P sub k in. But to find the k plus 1 term, I would say I have 1 plus 1 over 1 times 1 plus 1 over 2, dot, 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 times 1 plus 1 over k times the next term in the sequence. And the next term in the sequence is going to be exactly what the k1 is, except for you're going to change it to k plus 1. So do you agree that my next term for k plus 1 would be 1 plus 1 over k plus 1? Again, notice it's exactly like the last problem, except for it's multiplying instead of adding. And every single time it's the same. I can replace all of this with P sub k, because that's exactly what P sub k equals, which means I'm okay if you skip that step and you put P sub k times my next term, which is 1 plus 1 over k plus 1. But you gotta show me this step. Don't automatically plug in P sub k, because I want to know where it's coming from. I want to see that step. This one. This one. This step.
So, can we go ahead and plug in?
On the next step, yes, but show me this step.
Yeah.
That's what I'm saying. You can skip this if you don't want to show me writing the formula again. But you got to show me this. But then every single time, I'm going to replace P sub k. And again, if you want to circle this and show where you're getting it, this is what P sub k equals. So I can replace P sub k with k plus 1.
Where do you get the, like on the equation that we wrote it up in,
Mhm.
you get to multiply by the 1 plus 1 over,
This.
yeah.
That's where you have to know you're adding 1, right? P sub k is exactly what's up here. You have to say what is the next term. If this is the kth term, to find the k plus 1 term, you have to take what this formula gives you and change k to k plus 1 every time. So every time to get that next term, you take this formula and you change k to k plus 1.
You don't say it.
Right. You don't set it equal. You're just putting it down next to it. Once you do this, it's just all about making it match. We know that we want k plus 2. I think I need to get a common denominator here. Doesn't that seem exciting? k plus 1?
The original.
It was given to us, right? This was n plus 1. So that's like a given. And so you just change it to k plus 1. So that's why we say we assume that this is true. It's just what's given to us in the problem. Okay? This really isn't so bad. If I got a common denominator, do you agree that's going to be k plus 1 over k plus 1 plus 1 over k plus 1? And how do you add fractions when they have a like denominator? Like 1/2 plus 1/2, don't you add the tops and leave the bottom the same? So the bottom here is k plus 1, and what would I get on the top? Don't leave here when the bell rings, I'm holding you hostage. K plus 2, I just want to show you that this really does work. Because then I could cancel out these k plus 1s, yes? And I get k plus 2, which means I could say that this equals this, check mark. Your homework is different than your assignment sheet. It's shorter. You can only do this. Write it down. One. No, it's Korean. I'll send a note if you're late, okay? So don't stress. Write this down. Try then. You're not going to get better at it if you don't try then. Use your notes. It's really not the worst thing